I remember that I discussed on the inertial sensors. As an extension for inertial sensors, today I will concentrate on a particular inertial sensor which has got a lot of importance and application also, that is accelerometer. So, Micromachined Accelerometer for MEMS. So, I will briefly discuss on that. After that, I will go for a case study, detailed discussion on design aspects, development, packaging and fabrication of MEMS accelerometer for avionics application. Detailed case study, I would like to make only one device in this lecture series, that is accelerometer. So, it will take maybe 2-3 lectures, but today just for a background of that case study, I want to discuss on the accelerometers, MEMS accelerometers in particular, its classifications and its basic principle, and what are the various aspects of the accelerometer. Now, if I go for micromachined accelerometers, obviously a thing is coming in your mind, what is the different micromachined and conventional accelerometer? It is not that true that the accelerometers we are making first times in micromachined accelerometer, before that it was not there. For a long time, last 25, 30, 40 years accelerometers are there, but those are bulky accelerometers, conventional, and these are made of heavy metals, different small parts are integrated and to make those kind of accelerometers, and these are basically made from electromechanical principles. Mechanical parts are there as well as electronics is there, and each weighs several kilos like that, and it requires a higher operating voltage and also current. Obviously, you need larger power for those kind of accelerometers. It also needs careful maintenance and calibration time to time. Heavy mechanical structures are there, obviously maintenance part will be there, and with frequent use you need calibration of those devices after a certain period of time. Those are highly expensive because it is not throw away type. If something goes bad, it repaired because it is very expensive, and those bulk conventional acceleration sensors are highly sensitive, and it always gives large output in comparison to micromachined accelerometers. On the other hand, if you compare those conventional accelerometers with micromachined accelerometers, the following points are coming into our mind, that as those micromachined accelerometers are micro size, lightweight. Obviously, you are making use of silicon, small amount of silicon to make the complete structure. It is batch fabricated by advanced microfabrication technology. Because of that, obviously it will be of low cost, and it is throw away type. If something goes bad, you throw away, you take a new one. There is no chance of repairing those micromachined or MEMS accelerometers, which is possible in conventional heavy bulk microaccelerometers or accelerometers. Obviously, since the MEMS accelerometers are smaller in size, so it operates in a low voltage and low current, and so the power consumption is extremely small. That is one biggest advantage. When you are going to put those accelerometers, you need number of pieces for a microsystem, and individual piece if require a considerable amount of power, total power requirement of the system will be very high, and many cases those accelerometers are used either in avionics or aerospace or say missile program or anywhere. So, their power consumption an important issue. So, always people look for low voltage, low power circuits, low voltage, low power devices. Not only that, nowadays the time has come that everything operates in a remote control system, and not only that, many cases we use some handheld systems. So, those cases obviously power consumption is an important criteria. In that respect, the MEMS accelerometer has certain advantages. on chip integration, smart, intelligent and reliable. That is obviously an advantage, and is a great advantage, because you can on chip, on the device side, you can integrate its signal processing circuits, replacing majority of the conventional systems by the MEMS accelerometer nowadays. Now, there are three broad kinds of microaccelerometers. Obviously, there are other kinds which are not that much popular. I will discuss one by one. Out of the different microaccelerometers, MEMS accelerometer, three are very important, which are, one kind is based on piezoresistive microaccelerometer, the second is capacitive microaccelerometer, and third is tunneling current microaccelerometer. So, first two, piezoresistive and capacitive accelerometers, are meant for higher G's, but the third kind, tunneling microaccelerometers, is meant for low G, in some cases milli G or micro G level acceleration can be sensed by tunneling current microaccelerometer. So, the basic principle of those three I will discuss. This is one, the piezoresistive microaccelerometer in general form I am talking. There, what is there, you see, this is the substrate and this is the movable mass, and here is the cantilever beam, and this is the piezo resistor, and in the bottom place is a Pyrex plate is there. So, it is bonded, the substrate is bonded with the Pyrex plate, Pyrex glass. So, in this structure, if you fix the whole thing, this Pyrex glass is fitted rigidly on the body whose acceleration you are going to measure. So, then on movement of that particular body or system, then movable mass because of inertia will move either upward or downward, as a result of which, since it is fixed on this cantilever beam, so stress in the beam will change, and because of, if you put a piezo resistance there, so its resistance value will change, and that will be the measure of the acceleration of this kind of accelerometers. So, this is a very simple kind of piezoresistive accelerometer, but there are a lot of modification for getting certain improvement or certain specific performance of an accelerometer for specific application. Those I will highlight in subsequent classes. So, general structure is like this. Next, the principle is mentioned what I just told you. As the support frame moves relative to the probe mass, the suspension beam will elongate or shorten, which changes their stress profile and hence the resistivity of their embedded piezoresistors. These piezoresistors are generally placed at the edge of support rim and probe mass where stress variation is maximum. At the edge of the support beam, that particular edge or location you have to find out, and that require a rigorous analysis of the structure, that is stress analysis of the structure, that normally we do with the help of certain software. Now, this kind of piezoresistive accelerometers, if I compare with other kind, capacitive or say tunneling current microaccelerometers, so it is a simple in structure, simple fabrication process including their readout circuitry compared to capacitive and also to some extent tunneling. Tunneling is also simple, but capacitive is not that much simple. It is less susceptible to parasitic capacitance and electromagnetic interference. That is one important aspect. If you use those kind of accelerometers in space, then obviously the EMI EMC problem will have to look into, because of that some parasitic or stray signal you can pick up because of EMI and EMC problem, and sometimes if electromagnetic interference is much, so that may change the performance or total readout electronics or total the output which you are getting out of the accelerometers may change a little bit because of that problem. You have to take care of those, and it is also less susceptible to parasitic capacitance, and is also an important phenomena, because we know the output of those kinds of MEMS accelerometers are very small. Its signal is very much negligible in the range of the millivolt or microvolt. In case of current sensing, it is a picoampere or say microampere range. So, there you have to take care that parasitic signals should not be comparable with that means what, the output of these accelerometers. So, that is in that respect it has got advantage, since parasitic capacitance are not coming into the picture in case of piezoresistive cases, but it has got disadvantage also. Those are large temperature sensitivity, because we know piezo resistance because of the change of mobility. I will discuss in detail that temperature compensation as well as the temperature drift in case of these piezoresistive devices. So, with temperature lot of changes will take place inside the crystal, so far strain is concerned, so far stress is concerned, so far mobility is concerned. So, because of that the output may change, and that output will 100% not signify the input variation or G variation. So, that is one disadvantage. Small overall sensitivity than capacitive devices, small overall sensitivity than capacitive devices, and hence a large probe mass is preferred for them. If you want to increase the sensitivity of this kind of structures, one aspect is you have to increase the mass of the probe mass, and in that case it will be not much integrable compared to others. So, that you can say it is a disadvantage. If you want to increase the probe mass, obviously either thickness of the probe mass will be more or the area of the probe mass will be more, that means it requires larger silicon area. So, that is obviously is not a good point. So, temperature compensation circuitry is desirable in these kinds of sensor, which is not desirable in capacitive cases. So, now capacitive microaccelerometer simple structure is here. In this diagram you can see it. So, what is there is this kind of structure. The seismic mass is held with two these flexures, and the capacitance are made from the top surface of the seismic mass and upper cover, upper case, and another capacitance in the bottom surface of the cover plate and the bottom surface of the seismic mass. That means at the top there is a capacitance, and at the bottom also there is another capacitance. So, if you bond the middle structure along with the top and bottom the cover plates, then two capacitance C1 and C2, in one capacitance will increase, another will decrease. So, because of the movement, the probe mass movement, the gap, if it goes upward, the gap of the bottom parallel plate capacitance will reduce, and the gap of the top parallel plate capacitance, gap between the electrodes of the top parallel capacitance will increase. So, where reduce bottom one, the capacitance will increase, and top electrode this capacitance will decrease. So, that means there is a differential change delta C if we take the difference between one and other. So, that if we consider the differential techniques in this particular case top and bottom, then you can avoid some sort of the parasitic capacitance also. So, this is the basic structure of that, and here the principle is, in presence of the external acceleration, the support frame of accelerometer moves from its rest position. As a result, the narrow gap between the probe mass and the fixed conductive electrode changes, which in turn changes the capacitance formed between them. This change of capacitance can be measured using electronic circuitry. So, that is the basic principle. Now, there is another kind of accelerometers are available nowadays, which are basically the comb type accelerometers, and those are made using surface micromachining technology. And here this kind of structures are preferable when you want to integrate the readout electronic circuitry and the sensing part together over and at a small area on the top surface of the silicon. Here silicon is used as a spring and mass action, and you can use the interdigital structure, some fingers are there, and the fingers will make the variable capacitance. There are two things, one is the spring and the mass, and these are fixed outer plates. Okay. So, now you can see if this spring or mass, if it moves in this direction, so these are the fixed electrodes. So, there what will happen if this moves, so the some of the central electrode is fixed with that. So, if you say CS1 the capacitance of this part and CS2 is the capacitance of this part. So, the gap increases, so obviously CS1 will reduce and the here gap reduces, though CS2 will increase, this capacitance will increase. So, as a result of which you will get a differential change if this things moves there. So, it can be made if the interdigital in the surface also, and it can be made as a bulk also, both way possible, but is a preferable, it is easy to make using surface micromachining technology at the surface itself. And if you use the lot of fingers together, there will be lot of parallel capacitance if you add together. So, that total capacitance value will be more, and as a result of which your sensitivity change of capacitance will be more. That means small acceleration also you can sense with this kind of structure. So, that is interdigited kind of structure. In some cases there are two kind of methodologies followed. In some cases the mass and spring is fixed, so and these fingers are moving. In other case the fingers are fixed and the mass and spring will move, both are possible for different application, and both has got certain advantage and disadvantage. So, change in displacement basically is will change of displacement means it will change the gap between the two electrodes. So, as a result of which the capacitance will change, and that is also differential capacitance. You can see one capacitance will increase, another will decrease. So, that we need for removing or eliminating some of the parasitic things. Now, here the advantages are, is a low temperature sensitivity. Obviously, the capacitance, the principle of what I discussed, that is not dependent on temperature. So, low temperature sensitivity, good DC response and noise performance, low drift, high sensitivity and low power dissipation. So, these are the some basic advantages of the capacitive microaccelerometer. Disadvantage, obviously the parasitic components and the EMI, electromagnetic interference problem, which can be addressed by proper packaging. So, EMI EMC only can be eliminated by a special kind of package which will not allow to change the signal on the EMI or electromagnetic radiation, which is very high in space. So, now the capacitive accelerometer, they use the bulk silicon micromachining and wafer bonding. A silicon middle wafer is anodically bonded to two glass wafers on top and bottom to form a Z-axis accelerometer. The structure will have two different differential sense capacitors with the probe mass forming the middle electrode and metal on the glass wafers forming the top bottom fixed electrode. Air gap is formed by recessing the silicon on glass wafer. So, that is the wafer bond and silicon micromachining, both are required. Not only that, the glass recessing which is mentioned in the third point. So, that means you need micromachining of glass also before bonding. So, silicon as well as glass, both micromachining technique has to be standardized for making these kinds of accelerometer. Now, there is a second approach where we use the same scheme 1, but using all three pieces made of silicon. The first one is the those are made the two are glass and bottom is silicon, but in this case the all you can make silicon. This will reduce its temperature sensitivity, long term drift, incorporation of damping holes in the probe mass to control damping. So, by just damping is also an important phenomenon if you go for designing an accelerometer. So, their specific design is to be included to reduce the damping, because I mentioned earlier also, if damping is not there, So, it will take long time to stabilize the thing. That means its time constant, it will not be a very high speed measurement is not possible if damping is not provided. Not only that, if you do not apply proper damping, there is a chance of the resonance of the complete structure. So, as a result of which the complete thing can damage. So, for that is also this is important, and various kinds of damping incorporation or damping technology is considered in case of the accelerometer. In some cases only just using the top and bottom cover plate, and inside some ambient pressure is changed. In some time it is done in complete vacuum, sometime in different gas pressure of different viscosity is used inside the encapsulation chamber. Some cases you can make some perforation on the probe mass to have desired value of the damping factor. Use of second silicon wafer bonded on top to provide over range protection. These are the second approach, and third approach is surface micro-machined accelerometer offers the opportunity to integrate the sensor and interface circuitry on a single chip. It enables detection of very small capacitance variation less than 1 femtofarad, which is required for if you want to measure very low G. Sensor and interface electrons can be implemented in a small area. High precision accelerometer uses a combined surface and bulk micromachining process to obtain large probe mass, controllable and small damping, and small air gap for large capacitance variation. So, these are the 4 approaches, and for many cases depending on the infrastructure available in a particular laboratory, depending on the advantage, many out of the 4 something is selected for some application. Some particular method is selected for particular fabrication, particular kind of accelerometer fabrication. Now, the micro-machined tunneling accelerometer. So, tunneling accelerometer is also getting importance nowadays, because it has some capability of measuring very low G, and its basic principle is like that. It uses a constant tunneling current between one tunneling tip attached to a movable microstructure and its counter electrode to sense the displacement. You can see the structure here. This kind of accelerometer combines capacitive actuation with tunneling sensing. What is that? Capacitive actuation and with tunneling sensing. You can see here there are 2 pieces. One is the bottom piece which is blue in color, and the top the red along with this the green color thing. Now, here you can see in the top layer there is a cantilever, micro cantilever, and at the end of the cantilever there is a tip. This is known as a tunneling tip. Small yellow color here you can see in the figure is a tip. Now, in the bottom plate there are 2 patches are there. Those are for capacitive actuation. What is the purpose of that? So, now you see, by applying some voltage of this top cantilever is conductive kind of thing, or if it is not conductive silicon, so at the bottom of this cantilever is a gold coated. So, now by applying the electrostatic energy, this cantilever at the top can be pulled down to the bottom, can be pulled down to the bottom, that is known as actuation. So, by applying certain potential in the top patch and top electrode and the bottom patch, the gap of this particular tip with the bottom piece can be controlled, because we know the tunneling is only possible when the 2 electrodes, gap between the 2 electrodes are extremely small. Then with application of certain voltage, the tunneling current will flow. Basically, the gap between the 2 electrodes means here the small gap, there is a dielectric, the dielectric breakdown will occur, and through that you will get the current, and this small gap between the top tip and the bottom, the conducting patch, should be of the order of few angstrom, maybe 2 angstrom, 3 angstrom, 10 angstrom, like that, in that range. So, exactly making that gap would be very difficult, and not only that, if you want to have certain amount of tunneling current by electrostatic actuation, this gap between the tip and the bottom plate can be adjusted, so that you can have considerable amount of the tunneling current. After that you apply the fixed electrostatic actuation voltage. So, you fixed up this, that means this thing will the cantilever tip and the bottom gap is kept constant. After that, if you move this whole thing or it vibrates the whole structure, then because of the mass of that inertia of that top cantilever beam, the tip gap between the bottom and top will change, and that change is because of the inertia of the top cantilever, and then the tunneling current also will change, that is because of G. There are two things you remember. First, you have to adjust the constant tunneling current between the top electrode and the bottom by adjusting the gap, and that is normally done by electrostatic means, the actuation, capacitive actuator, we can say it. So, after that you fix the whole thing in a body whose G or movement or vibration you want to measure. Now, because of the movement of that, the small gap between the tip and the bottom plate is going to change, and then tunneling current also is going to change. Okay. So, this is the basic principle. Now, one of the dimension is shown here. This is the base where the tunneling tip is fixed. These are the two patches, and here is a basically the tip is here. There is 60 micron width is the cantilever beam, and these are the horizontal and lateral dimensions of the structure is shown. And now, if you concentrate the working principle, so what are the steps followed? First is, as the tip is brought sufficiently close to the counter electrode is at the bottom, few angstrom, using electrostatic force generated by bottom deflection electrode, a tunneling current is established and remains constant if the tunneling voltage and distance between the tip and counter electrode are unchanged. Is clear? After that, step 2, once the proof mass is displaced due to acceleration, the readout circuit responds to the change of current and adjusts the bottom deflection voltage to move the proof mass back to its original position, thus maintaining constant tunneling current. So, you see this approach. Change of current is very difficult to measure. So, what they are doing? So, because of that acceleration, the tip is going down and the current is going to change. Now, what we can do, that the electrostatic energy which is applied the patch to, that is electrostatic actuation, drive voltage is there, so that whole the cantilever goes down or up. So, that voltage you change, so that the gap also can change and it maintain the same tunneling current. That means constant tunneling current is desired, and how we are maintaining the constant current? By changing the voltage between the two patch, that is electrostatic drive voltage. So, that change of voltage will be the measure of the acceleration. Always in any of the signal conditioning or signal processing circuit, change of voltage is very easy to handle rather change of current. So, that is why you can get the change of current, but that is not the final thing, you have to process that signal. So, in there we know if we convert into change of voltage is easy. That is why what they are doing here, the current remains constant. Now, adjust the bending, we can say that the voltage required for adjusting the gap, so that the current is maintained constant. because of the accelerating current change, now the gap can be adjusted by adjusting the voltage, driving voltage between the plates, so that current again remains constant. So that is the principle used in this kind of the tunneling current microaccelerometer. And the third step, acceleration can be measured by reading the bottom deflection voltage in this closed loop system. That is what I told you. And this kind of tunneling accelerometer, the application areas are space, defense, seismic science and upper atmosphere. Seismology, so very feeble vibration of the earth, so that normally is monitored with the help of this kind of tunneling accelerometer. In other than space, defense and upper atmosphere application, this is one of the vital application of the seismic in case of seismic science. Now, as the tunneling current changes by a factor of 2 for each angstrom displacement, accelerometer using this principle achieves very high sensitivity and capable of measuring micro G acceleration. This is the basic essence or advantage of this kind of accelerometer. These devices have large low frequency noise level of the order of 4 millig per hertz at 0.5 hertz and 0.1 millig per hertz at 2.5 kilohertz. These are some of the salient points of this kind of accelerometer. There may be advantages, may be disadvantages, but this is the thing we get from this kind of accelerometers. Requirement of high supply voltage 10 to 100 volt limits application of these devices, because you see the why high supply voltage, because you have a whole cantilever, the actuation is done by electrostatic manner, because the whole cantilever, the bending of that cantilever or releasing the cantilever, so that is done by electrostatic voltage. That voltage may not be very small, in the range of 10 or 20 or 12 or 15, or in some cases it depends on the tip dimension, how fine you can make, how close gap you can make, and how thin the cantilever thickness you can make, because all these parameters will decide how much voltage you require for deflection of the cantilever beams. So that is one kind of the disadvantage, you need the high supply voltage for, because of the electrostatic actuation. Now, the basic principles, if you look, then when two conductors are brought into extreme proximity of the order of 1 nanometer with an applied bias between them, electrons will tunnel across the gap. That is the tunneling principle. The equation for the tunneling current is of the form I tunneling, which is proportional to V tunneling dot e to the power minus alpha x under root phi. So this relation is known Simon's relation, and detailed derivation is given by Simon, and in this expression I TUN is basically tunneling current, V TUN is tunneling voltage, alpha is the tunneling constant, and phi is the tunneling barrier, x is the separation. Phi is the tunneling barrier, it depends from the gap and dielectric constant of the two in between two electrodes. So this is the relation between the I tunneling and V tunneling with two constant, one is alpha and phi, which one case is tunneling constant, other is tunneling barrier. Tunneling constant depend on so many parameters and of the structural parameters, and that is why altogether we wrote it is alpha and is a constant for a particular device. Now, the thing is that what are the basic advantages, means why the tunneling accelerometer we go for. Although it is a very critical, fabrication is not so simple like the capacitive or piezoresistive accelerometers, but even then people are going for this for specific reasons, and those are mentioned here. First is it reduces cross axis sensitivity. Cross axis sensitivity means, you know, if it is meant for one axis, the other axis sensitivity will not be there. That means it is a vertical, because it depends on the small gap between the tunneling point and the base plate. So that is one direction only. If you can make the tip and the base point, the electrode, that is very small amount, very small size, and tip dimension may be of the order of say few angstrom, 4, 5, 6, 10 angstrom tip, so that in other direction it will not sense. Modeling simplicity, high natural frequency, these are all its plus points. Well damped bending mode for faster transient response and small settling time. Low electrostatic voltage requirement for DC deflection and self test, that also depend on your structure. If the structure is big and the flexure dimension you cannot make very fine thin, so you have to go for high voltage also. High bandwidth, less noise effect. So these are some of its advantage. Now any kind of the accelerometer you will be developing, you need certain steps for analyzing this kind of accelerometers. What are those? It is not only accelerometer, any kind of MEMS devices. The basic steps for designing is as follows. First you have to go for a layout, tentative layout, tentative structure you have to think from your specification. So after finalizing the tentative layout, that is may not be final, tentative I call. So after that you have to go for process definition. That means what are the steps you will follow for making those devices. Then you have to go for 3D model, because the small structures you need always 3D, because these are MEMS are all 3D devices. So there you need 3D solid model, you have to build that, and for modeling that obviously it will not possible to model this kind of structure using the linear equations or quadratic closed form analytical solution is not possible in any kind of structure. That is why you have to go for meshing. Meshing is required for what? For finite elements or numerical analysis of those structures. Then after meshing you have to go for the mechanical analysis, and mechanical analysis may make some software tools are available, ANSYS some another software tools is also available. So either using those, not only that, various nowadays kinds of the numerical software tools are coming into the market, you can use any of them after proper meshing. Then you have to do the mechanical analysis, which we call MEMS, because any kind of this kind of sensor, there is mechanical movements will be there, that is reflected into electrical signal pickup, that means electromechanical system, the complete thing. So you have to go for MEMS, which is mechanical analysis. Then electromechanical analysis, the mechanical analysis next step is electromechanical, so that you can go for the electromechanical. After electromechanical analysis you may get the electrical signal or electrical output or other things, that is co-solve, which is electromechanical analysis. So these are the steps normally follow in case of the MEMS analysis of any of the structure, any of the devices. Now this is one kind of the steps or methods we follow in case of the tunneling accelerometer. You can see the mesh, how the mesh is defined in these cases. Mesh size may be different for different kind of structures, that also I mentioned sometimes back. So that is where you need the much more regular analysis. You can reduce the mesh size, so the number of elements will be more, you will get much accurate analysis, and after that you can go for increasing the size of the mesh, so the number of elements will be less. As a result you can get the some kind of time management, because your analysis will take time, more time if you go for higher number of elements. So now here the two structure are there. You see obviously the top structure where the number one is the cantilever with its integrated tip. So here is basically you are getting this the stress in this cantilever. So obviously here the structure of the mesh should be designed or fixed accordingly. So small size structure. The bottom is this is the bottom second one, the base of the accelerometer. There you may go for the larger element size. Now So, here are some results of the tunneling current behavior and electrostatic actuation. You can see here the tunneling current versus acceleration is plotted. You can see is a point up to 0.1, 0.2, 0.3 G, the current is almost negligible. That means the G higher means obviously the tip movement is more. So, hence tip movement is more. So, you can get after the 0.4 G to up to 1 G. You can see after 1 G it is a rapidly increasing the tunneling current. Obviously, current is in the order of nanoampere. So, this because that means it is sensitive after the 0.4 G so to maybe 1 or 2 G. Here this region is linear almost, and if you look into the deflection voltage versus deflection, that is also plotted here using the analysis of finite element analysis. So, deflection versus voltage and the voltage required to maintain the constant current, or the if you apply this voltage, so how much deflection of the tip will be there, that is electrostatic actuation, that is plotted here. So, you can see is a not very high, say 4, 5, 6, 7 or 8 volt is there you can have the deflection from 400 to say 2000 angstrom in that range. So, this is the deflection versus the voltage. Now, you can see here the some of the figures generated from Coventor simulation. So, displacement is here, you can see 2.6 to 5 10 to the power minus 4 centimeter. So, that is the displacement of the tip, and here is the stress developed at the tip for different acceleration. So, this kind of pictures you can generate from the Coventor software. Now, these are the tunneling accelerometer process flow. So, there are two pieces, as I told you, the bottom and top. The bottom is base wafer and this is a cantilever wafer. First what you did, you took a n-type 100 silicon wafer and then you go for thermal oxidation. The both top and bottom is oxidized, oxidized layers are here, you can see. Then after that you are depositing the metal, the patches in the bottom 1, 2, 3, 4. So, these are the patches, base electrode fabrication. Now, in the other side, the top is the silicon epi layer on n-type 100 silicon, that is for top tip fabrication. Then you define by dry etch, the epi layer is defined here. Then after that you just again form the base point where the cantilever will be fixed with the other part and the tip. The tip formation is highly crucial. So, after making the two piece, then this piece is inverted and you just put upside down on the base. So, this and these are the two pieces. Now, this you make upside down and place on the top of this, and then you fix, this is a metal and this is a metal, the gold foil that will be fixed here. So, that means, and these are the electrostatic actuators and this is the tip and this is the gap of the tip. In this way you can fabricate this, the tunneling accelerometer, and these are some of the photographs of the tip, and the tip looks like that. Making the tip is highly crucial. You can see here the oxide mask, then you have to etch some kind of V-groove etching, and then the tip of the group is something like that, pointed tip, and then how it is inverted and fixed top and bottom, that is also shown here. Now, there is another two kinds of accelerometers are there, just I take 2-3 minutes. So, that is Micromachined Resonant accelerometer. They use a resonant silicon cantilever beam. Silicon resonant accelerometers transfer the probe mass inertial force to axial force on a resonant beam and shifting their frequency. So, here basically the frequency change is the observation for variation of G. A differential matched resonator configuration helps to cancel device thermal mismatches and nonlinearity. So, this kind of sensors obviously free from any thermal problems or the parasitic capacitance problem, etc., because you are not directly dealing with the capacitance, but directly frequent structural vibration etc., that frequency is going to change, and one example is quartz micro-machined resonators. So, these are the thermal transduction mechanism, that also I told you. The temperature flux from heater to heat sink plate is inversely proportional to their separation. By measuring the temperature using thermopiles, the change in separation between the plates can be measured. Change in separation between the plates is representative of the acceleration. Accelerometer with fixed heater and a moving thermopile away or vice versa may be fabricated. That is not very much popular, the thermal transduction mechanism. And last is the packaging. Package criteria of accelerometer is also very important issue. Protection of sensor structure without inducing significant stress or drift, because package should not produce additional stress or drift. Proper mounting without misalignment, otherwise it may affect the sense direction and overall performance of the device. Should not affect adversely the sensor frequency response or temperature sensitivity. These are the 3 points which you have to look into in details before going for packaging. Okay. So, with this let me stop here today. So, in next class I will just concentrate on a case study, first design, then analysis, then fabrication. Thank you very much.
1951. A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today IIT Kharagpur has blossomed into a time-tested, venerable institute of learning. With the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theatres, and from the quiet fiber optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus, but its diverse range of activities. It offers the widest spectrum of disciplines, ranging from aerospace, biotechnology, cryogenics, to architecture, mining and agricultural engineering, supported by strong faculties of sciences, humanities and management. There are more than 30 departments and centers that offer the largest number of undergraduate and postgraduate courses amongst the IITs. The courses are ever evolving and show the way for other sister institutions. The richness in its diverse activities is showcased by the technological support the institution provides in areas like architecture, agriculture, post-harvest technology and medical sciences. The institute has revolutionized and popularized rice milling technology. The other major contributions of IIT Kharagpur have been in the critical fields of defense, railways, space research, power systems and petrochemicals. All these activities directly empower the human requirements of the nation. Advanced facilities at the Institute make it possible to undertake cutting-edge research and service-sponsored research projects. The array of equipment ranges from aerodynamic testing laboratories to intelligent machining centers, atomic spectrometers, to VLSI design labs, molecular beam epitaxy, to anechoic chamber, fast protein liquid chromatographs, to liquid nitrogen plants. The cutting-edge technologies are at par with the best research facilities across the globe. In fact, the volume of research and development activities at the Institute is incredible. In terms of the number of patents it owns, the volume of industrial consultancy it provides, and the revenue that it earns from all these make IIT Kharagpur a class apart and strengthens its position as the true pioneer in technological education in India. The Institute Library deserves a special mention. Fully web-enabled, it is one of the largest in Asia with over 324,000 volumes of material, including books, videos, microfilm, and patent documents. champions that ensure a student's mind develops at the right pace. Along with its strong sense of academics, which is ensured by a strict selection process, life at Kharagpur is a celebration of, well, life. And at its heart are the students. In fact, the saying goes that you can take an IITN out of KGP, but not KGP out of an IITN. You've left a part of you behind. For most of the students, life in the campus was in itself a festivity, a collage of activities that shape their mind and body, a collage of events that was a synthesis of competition and cooperation, a collage of interests as diverse as dramatics and ham radio. Yes, life at Kharagpur has always been exciting. And the years cemented lifelong bonds as lives mingled over cups of joy and stretched over stimulating semesters. The halls, with their blocks and wings connected by charming catwalks, remain ensconced in their own world. A collage of memories. Infrastructurally adequate, architecturally meticulous. Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.